Hello everyone, it's November the 21st. Today was a frustrating day. I bought a bike from Walmart, got shipped last night. Very excited, trying to put it together today. And the bike was defective, right? That was the fork dropouts, they don't align with each other. So when I try to put the front wheel onto the dropouts, I just couldn't. I cannot fit it in there. And I think I wasted like maybe an hour, maybe an hour and a half. I tried to see if I can bend the fork to make it align with the wheels. It didn't work. It did not work. Yeah, very frustrating. Then I try to return it. The bike is huge, right? It's a huge item. So I tried to schedule for a FedEx pickup, but then Walmart, being Walmart, said, they had issues scheduling an appointment with FedEx. I like, screw that. I'm just gonna return it myself. It's all fine. It's fine. Things like this happen. I mean, I knew it. It's not gonna be good because this bike was selling for about what, like $50 cheaper than I was supposed to. I mean, with these type of purchase, it's a hit and miss, right? It's always a hit and miss. But because of this, I got frustrated. So I went online to search for a new bike and see, watch some more videos, do a little bit more research into it, and I just realized one thing: why did I even buy it? Like, the one I bought was a mountain bike, right? Why did I buy a mountain bike in the first place? I mean, mountain bikes look cool, right? With all these multiple speeds, right? With a disc brake or whatnot, it looks cool. But man, that is a lot of components, right? A lot of components. And then I look at those single-speed bikes, those old-school single-speed bikes with a coaster brake. Man, those have no cables, right? So we're talking about single-speed with a coaster brake. So it's easy to ride. Like, for me, I'm not really a cycling enthusiast, so it's easy to ride. You can coast and you can brake by backpedaling. So there's no brake pedal on the front, no cable, nothing to maintain, single speed, none of those discs to go wrong with, right? So at the end of the day, I just asked myself, what is more important, right? Is it to have a cool looking bike, or is it important to have something that I can commute with? That's what I'm trying to do, to commute using a bike instead of driving that much. So the answer is straightforward. It is to find a tool that is easy to maintain. Think about like programming, right? You write something that's easy to maintain with the minimum amount of features that you need, the core features that you need, and will be easy to fix. Like, I also watched some videos to fix, say, a rare coaster brake. It's not that difficult to fix by myself. So at the end of the day, it's always like functionality should trump how the thing looks like. I mean, there are cool looking bikes out there and also function well and durable, but those cost way higher, right? We're not like, my budget say like maybe $200, but those are good looking and functioning bikes, so it cost $400 or $500. Like, that's out of my range. So that's that. It's some revelation. I mean, yeah, exactly. Why do I want a cool looking bike? Right? What's the point? What is the point? There's no point. The point is just to get something that works, right? So, yeah, so that's that. I got a little bit frustrated earlier today. But anyway, let's go into what we have today. Something we've done before, so hopefully it shouldn't be too much a challenge. Alright, construct binary tree from in order and post order traversal. Oh, in order and post order traversal. I think I've done this before. Yeah, just recently, a few months ago maybe. my recollection is always wrong. A few months? Come on, man. That was like more than a year ago. July, right? It's all July. Like, every time the recycle problem It all happened back in July. Okay, so I have a pre-order and I have a post-order. No, not pre-order, in-order and post-order. In-order is the in-order traversal, post-order is post-order. Construct and return the binary tree. So I have an in-order, I have a post-order, and I return it. Blah, 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 length the same. That's the value. Unique values, each value of post order also appears in order. In order is guaranteed to be in order, post order guaranteed to be post order. Alright, so what is in order? 9, 3, 15, 27. So it's what, left, root, right, right? Left, root, right. Left, root, right. Post order. Wait, what's post order? Left, right, root. Left, left, right, root, root. And we need to build a tree out of this. How did I do it? I just don't know. I mean, I say I like trees, but building the tree is always tough for me. So in order is left. So left, root, right. So left, root, right. And the post order is left, right, root. I'm drawing blank right now. Let me think. Left, root, right, then left, right, and root. So left, right, root. So we know the root node, it must be this one, right? That must be the root. And then that will be left something, right something, whatnot, and then root. And because of that, I will be able to know where the root is inside. How do I know where the root is inside? So this one, we know the left. So we know the left, right? So let's be the left. And then we root, blah, 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 blah. So if I can find, but nothing is sorted, and we have 3,000 nodes. Are you saying we're gonna look for the root, go in there, find a root, right? Because the left, root, right. So I can split into left and a right. Now within the left, yeah, I can find the root. So I find the root is 3 from post order, right? I find the root is 3. So I can divide by in order a left part and a right part. So left part, this one will be 9. Right part is 15, 20, and 7. Now we need to find the root for the 9 part. How do I find the root for 9 part? Is this one on the left, right? And then when left is done, I go right. Okay, so left, right, root. Therefore, if I can find in here 15, 7, 20, 15, 7, 20, so these will all be together, right? So 15, 20, 7. I know 15 is the left, and because in this post order, left, and right, and then root. So 15 is the left, so we can find the left as well. The left will be 15, right? And then what? So left, right, root. So the root will be 20. How do I know the root is 20? Well, because 3 is the root, and I remove 3, right? So the remaining the remaining thing, 20 must be the next root, right? So if 20 is the next root, I will say look into here, right, to find where 20 is. So 20 is here, so in the right subtree. So the right subtree I have 20. So I can get 20 out. So I can split that into 15 and a 17. Right? And then what? And then I look for the next root. Next root is 7. And then we find 7. And that's it. Next is 15, and we find 15. That's it. And next is 9, we'll find 9. And that's it. Hold on. So are you saying we use post order to find the roots? That's true. We use post order to find the root. And we use in order to split it into two parts. How do we write this? I mean, specifically, we'll have to traverse the entire thing to find the root, and it'll split into two. Alright? And basically, we say we split into two, and this I can just pop it. And then split into two, we'll go right subtree first. So I'm in the right subtree. So I am basically saying I have a in-order traversal of this, and I have a post-order traversal of this. How do I handle it? So I say I had 20. So I again look for 20. When I look for it, I am going to go to the left and the right, and go right first. When I get it right, I'm going to pop the next root, right, and I look for it, and we find out we only have 1. So I add it, that's it, that's n, and then we'll go, and then we'll pop. Actually, do we pop it? I mean, we can. It wouldn't be better just to use an index, right? So we don't have to pop anything, okay? So next is 15, which is actually going here, which is done. And then I think that is the case. And since we only have 3,000 in length, so I guess it's fine. Alrighty, I think that is the way to go. All right, let's do this. One. This is actually pretty tough. I did, like, kind of vaguely remember when I done this question a year ago. I remember it was not like those easy peasy thing, right? It was not. I remember I had my struggle. Alright, so we do this, then we do, alright, so what do we do? So we need a def build, okay? So what do we need? We need index, right? So we need a low and a high. So we have a low, we have a high, and we have a low and a high. What else do I need to return, right? I need to return a tree node. Right. So I say if low is equal to high, then I just return tree node in order low. I say val equals, right? That's it. Well, actually, I also need to do this. Self.pi, right, equals len post order -1. So every time I visit a node, right, every time I call the function, that means I visit a node. And that must be a root node. So I need to do pi -1. Then I do all this. Wait, do I -1 now or later? So I'm gonna do this, right? Then I need to find the thing. You know what? I shouldn't do it now. I should do it later. We'd do it like that, right? Otherwise, then based on current PI, we're just gonna look for, right? We're gonna look for I in range, right? Low to high. Say if in order I is equal to post order self.pi. If that's the same, then what? And then root equals to tree node, val equals in order I, right? Val equals in order I. And once I got that, we can actually, hold on, this actually, you can do it even cheekier. I can just say, this is this, we can go left. Actually, we're gonna right first, right? Oh, let's not do this. Yeah, let's do this. Right will equal to, right will equal to build. This is I, right? So it's I plus 1 to high. Oh, where are you going to decrement P? P is constantly decrementing, right? P is constantly decrementing. So basically, once I find it, then self.p I need to minus equal 1, right? P decremented, then right will do this, and it will be decrementing as we go. Once we're done, do I need to decrement again? That's a good question. That is a good question. No, I think because currently that is the current root, right? And I decremented, that will be the next root. We're finding here, right? And after I find the next root, do I decrement? Yeah, because every time I call the build, I will decrement, which means after I return, it has already been decremented. Which means I don't have to decrement again. I just go build again. That's going to be 0 to I minus 1, right? And let me think again. Do I have to do 2 times decrement? No, I shouldn't do 2 times because for each time in this recursion, right? For each recursion, I am interacting with 1 PI, right? And after I do that, I just decrement it. I say I used it, right? And then I go left and I go right, or not. Doesn't matter. And once this is done, then we're gonna return root. All right. All right. So now the question is it possible for us to simplify this? Because I have the duplicates, right? We have this here and this here. Well, I don't really think it's possible to I think this should be it. And then what? And then we're gonna call we're just gonna return build, right? 0 high. What is high? This is in order. So len in order minus 1, right? And that's it. All right, let's give it a shot. run code. You're running? Yeah, I think it is running, but it is super slow. Oh, did I do it 2 times? Actually, we can run both. Let's do both test cases. All right, be patient. Don't click it twice. 1 time is enough. Oh my god. That was terrible. Ha! What is the problem with myself? Okay, so we didn't do anything. All right, we didn't do anything. What the hell? Okay. I need an explanation. Output, I only have 3. So root is equal to 3. Oh! Ah, you stupid piece of crap. Yeah, that is really crap, man. Sorry. I don't know why I did that. Ain't right. That's not right. And 3 come out again. That is interesting. I think it's because the PI got decremented too much. Right? Alright, so what we did do is I got 3. I got 9. I got 20. Right? I got 15 and 17. Then I got 9 again. What is this? Why would I get 9 again? And once I reach it, I'll do all this thing, right? Let me see. This one minus equal 1, right? So self.pi, we go to point to 20, right? So we current point to 20, and then I do the right side, right? I do the right side. So on the right side, I is 0, 1, 2. So move 2 to the end, right? 2 to the end, coming in, low, high, not the same, and I'm going to low to high, okay, and we're going to find 20, and boom, I found 20, right? I found 20. I will be here, so root equals this. That's good, and pi minus, so pi now is here. Then I go right again. All right, I go right again. So I plus 1 to high. Now this one, low is equal to high. So I say pi minus equal 1, so pi now pointing to 15. Then I return this. So good, right? I got 7. Now I go left. Left is, oh, it's not 0. That is the problem. There we go. Alright, this one shall work. But I'm not sure I can hit 56. See how it goes. 480 milliseconds. That is ridiculously slow. So we need to figure out. Oh, I think, hold on. Why do I do this, right? What if, yeah, I can turn, I can do, let's see, I can do a hash map so I can find their index faster, right? So I can say, whose hash map? So post order is 1 by 1, so I need a hash map for the in order. So we say in order indices, right? Index. will equal to this for I vowel in enumerate in order, right? So for this, I'm going to say vowel I. So now we know the index. Right? Now we know the index. So now we do this. This is the same, right? Nothing changes here. But here I don't have to do this. I just say I, right? I will equal to what? Equal to in order index post order self.pi, right? I'll do that. And once I do that, I don't need to do this. I can go directly like this. So I get the root, right? And I got this. Okay, can we combine these two together? Yes. Yes, we can. I just need to say if low is larger than, right? If low is larger than, then we simply return a none, right? And now we find the index, we grab the index, and we do this, right? And we build right, we build left, and then return. That, I believe, will be faster. So, okay, so we try this again. Make sure everything still works, which did definitely work, right? All right, let's try this one again. Now this is yes, 60. Now we're talking about this is what's the runtime? So this runtime is on, and the build is actually is on. This one runs the on. This is what LeetCode. This is a good question. Very good question. 106. 106, right? A very good question. Very good question. I did it more than a year ago, but this time I knew I hit the right direction from the beginning. I almost hit. You did not hit the right at the beginning. I almost hit the right direction from the beginning. So the idea is to use the post order to locate the root and use the in order to split the building, right? To split the building into left and right subtree. The one trick to do the one trick is to use a hash map to quickly query the index of any root value in order array. I don't know why would I think I have to loop it, right? I mean, there's a hint in the question that it's unique. And whenever it's unique, that's a hint that you can use hash map to do this. And we hit a 60 milliseconds. If I remember correctly, that's a 73% ranking. I am not going to read the discussion because I'm pretty sure it's the same. So I'm going to check this one, and I just go clicked the discussion. Let's read the discussion. Recursion, most intuitive, blah, blah, blah. Don't use top voted. What's the top voted? That was a long time ago. The top voted, the pop, do this, in order the index, yeah, that's slow, right? That's slow. You need to use a map, exactly, and also ideally you should not pop, right? Yeah, I mean, I will not recommending popping because you're changing the input, right? If we can, try to write pure functions. So I think it's the same solution as last time. I have the index map. I have a p index. That's the same idea. If this, return none. Otherwise, root value, root index, and I don't know what this one is. Check the right first, the left. Yeah, it's the same thing. It's the same thing. All right, so we're done with today, but I have gone. Let's do one more. I think 2 questions is good. 3, maybe if sometimes I want to do easy ones, I can hit 3 easy ones, but usually medium is 2 for me right now, at least. Yeah, who knows? Maybe that's how we can gauge the improvement, right? So I think I'll be able to do 3 easy ones in one sitting, but maybe only 2 right now for one sitting. But in the future, I think once I can hit 3 medium ones regularly in a sitting, in a session, I might be able to just say, let's crack a difficult one. All right. Maximum square. Okay, let's not read this. Let's just close this. So maximum square is n by n, 0 and 1s. Find the largest square contains only 1s and return its area. Ooh-wee. That is an interesting problem. Maximum area that contains only 1s. Or it has to be square, the largest square, right? So we talk about 1 by 1, 2 by 2, 3 by 3, and the limit is 300, right? So the maximum is going to be, what's square root of 300? 18? Is that 18? Okay. Actually, I don't remember. What's 18? 18 square, 18, no, 18 is more, it's 324, 17. 17, so the maximum is 17, right? The maximum is 17. But how do we know? Let's see, what is the character? Maybe this is one of the application of prefix sum, but it's a 2D prefix sum. How about we go down that route? 2D prefix sum. Man, the example is just so complex. I have to draw the entire thing. So we have 4 rows. So 1, 2, 3, 4 rows and 5 columns. So 1, 2, 3, 4, right? So I have 1 on the first, and I have 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0. All right. So the prefix sum, a 2D prefix sum. Let's do a prefix sum on the rows, okay? Let's do a prefix sum on the rows. So on rows, the prefix sum will return the first row will be 1, 1, 2, 2, 2. Second row is 1, 1, 2, 3, 4. The third one is 1, 2, 3, 4, 5. The fourth one is 1, 1, 1, 2, and 2, right? So that's the prefix sum of the rows. And we also want to do prefix sum along the column, right? Therefore, at each position, we will have the sum of this square, right? It's not just square, like at each position, we know the sum of the entire thing. Let me think if that's correct. So if we have this, that's the total sum of this, total sum of this. So I just add these two, right? So when we add these two, so this will be 2, this will be 2, add these two, that's the total sum. Okay, so we just add, we add these two, so I'm here, right, I need to add this one and this one, right? Yeah, I think so. So So it's a prefix sum on a column. So first column is 1, 2, 3, 4. That means if we are here, this entire thing will be 4, right? Second one, 1, 2, 4, 5, right? So if in here, that's going to be 5. That's true. Third column, 2, 4, 7, and 8, right? 2, 4, 7, 8. That's true. The next one is 2, 5, 9, and 11. Next one, 2, 6, all right? 2, 6, 11, and what's the last one? 13. Oh, my handwriting is bad. All right, so now I have the 2D. So total is 13. I'm checking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, now we have the 2D. Now what do? We want to find the largest square, right? The largest square. I mean, we just need to search, right? What do we search? So given a position ij, right? Given a position ij, if we want to find the sum of a square, then it must be this ij, this whole thing, right? The 2D sum minus this, and plus this, right? So I can go through every single. I can go from the maximum, right? I can go from maximum, so it's 300. So I go from the minimum of m or n, right? I go from the minimum of m or n and search down. That seems stupid, right? That seems stupid. I mean, first of all, to make it possible, right? Let's say we want, because the area is the total number of ones, the sum of all that, right? So as I go through, I can record. So this will be the value, right? This one for this problem, my value is 13, right? My value is 13, and if the value is 13, then the largest possible is 3, right? The largest possible is 3. We cannot get 4. 4 requires 16. So our search is going to be 3, right? When we search for 3, see if 3 works. Now, how do we get 3? So we're going to go 3. So we're going to start searching with position 2, 2, right? So we're going to start with 2, 2, 2, 3, 2, 4. So we're going to search on this tiny amount, right? This tiny amount. So we're going to search, see if this is 9, if this is 9, if this is 9. And each search is 01 because I already computed, and this position is 7, right? And this position is going to be 9 minus 9 minus 3, right? That's 6, right? This position is 6. So that we can do an easy computation. So for each one, I'm going to search. So I search for 3, and do we have like a binary search scenario in here? Like I don't have to go one by. No, I don't know. I don't know. Binary search. It's not sorted. Nothing is sorted. Right? Nothing is sorted. Hold on, let me think. 11 will be minus 4, right? That's 7. Yeah, that is 7. And we do not know, right? We do not know. So if I go one by one, if the whole thing is gigantic, right? If it's gigantic, and I have to go one by one, that will be m by n, right? M by n by something. And of course, if it's the possibility is huge, then maybe this will work. I don't know. I feel like I'm on the timeout on this one. 300 by 300. N by n. That's 9,000. Runtime 9,000. Usually it's fine, right? Usually it's fine. I can set a higher bound, right? And we have a lower bound. We have a higher bound, we have a lower bound. What if we go binary search, right? So binary search, we go to the middle, and we say we find it. What does that mean? That means there is a full, right? A full ones with the middle size, and we find it. Then we can go find higher. Yeah, I think binary search might be working, right? So we don't have to go one by one. We can go to the middle, right? And it works, so I go search for higher value. If it doesn't work, that's true. That's true. If a given, right? If a given size of the square, and it doesn't work, there's no full ones in that square, then it's impossible because I'm searching every possible square of that size, every possible square, and I search for all of them, and none of them give me all ones, right? And if that is already no possible, then the bigger one will definitely not be possible. So definitely we're going to go binary search on this. So it's going to be a 2D, right? 2D prefix sum with binary search. Let's try this. 2D with 2D prefix sum with binary search. Now 2D prefix sum, that one will take OMN because every single one has to be visited. And the binary search will take, geez, I don't even know what binary search is going to take. Log something. All right, it's going to be log something. Oh, and that log something is not on top. Log something mn. So total runtime would be log mn, right? Worst case scenario. Okay, so all right, I'm gonna change in matrix. Although I said I don't want to, I guess it's not what is good, but it's fine. So I'm gonna do 2D, right? 2D prefix sum. So how do we do this? We're gonna say for row in matrix, right? And then for I in range, and usual I should have mn equals len matrix and len matrix 0, right? So for in range 1 to m, no, 1 to n, we say matrix, no, not matrix, it's row. Row I, actually, I don't like I, it's actually column, so row j. Row j plus equal to row j minus 1. Alright, so that's prefix sum. And once we're done, that's just done on each row. Now we're going to go column wise, right? So column wise is going to be for I, no, for j in range n. So now we have the first column for I in range 1 to m. Alright, now we say matrix. Why don't we just combine these two into the same syntax? It'll be easier, right? It'll be easier. So I just say for I in range M. For J, right? It just be matrix I J plus equal to matrix I, right? And this one reverse. So matrix I J, right, plus equal to matrix I minus 1 J. So this is, we do the, and then we go to binary search, right? So binary search. Low is going to be 1. Depends. Depends. Low is actually going to be 0. Because it could be 0, right? It could be 0. So low is the count, is 0. Now high, oh, hold on. Low, what does low mean? Well, we can actually do, Jesus Christ. I just realized these are all, oh, screw you. Seriously, screw you. Alright. Alright, screw you. Prefix sum. Yeah, I'm doing it. I'm literally doing it. 0 times. I don't know. Should we do it? No. I'm gonna change matrix. I am going to change matrix. So we can just gonna go matrix I 0, right? Equals to int matrix I 0. And every time this one will equal to int plus matrix I J, right? So now we're gonna do the same thing. Yeah, so now gonna be plus equal to this. Oh, hold on. This one is actually fine. Because I already turned everything into int here. Okay. So low is this. High is equal to actually low high. High is equal to matrix m minus 1, n minus 1. That's the highest we can get, right? Now, while low smaller than high, right? So while low smaller than high, mid equals to low plus high divided by 2. And then we're gonna search, right? Then we're gonna search. So we're gonna pick mid is the length, right? That's the length. Is that the length? Actually, high is not equal to this. High is equal to, I'm going to do the length. That's the length. Import math. I need int math.sqrt. High is length, so mid is now the length, right? And with this length, I can go the starting position, right? Starting position. So we just say for starting position for I in range something to m, right? For j in range something to n. Now what is the something? This something is going to be mid minus 1 and mid minus 1. It's like if it's 3 by 3, we're going to go 0, 1, 2, 0, 1, 2. That's our starting position, ij, right? And then for each ij, we're going to say if the area equals to something, and we say if area, right, is equal to mid times mid. We can actually do this. So target equals mid times mid. So we just say if area is equal to target, then Ooh-wee. Break. Hold on. We're looking for every single one. If we have found one, right, then we need to change. If we find one, then low will plus one, right? Low will be mid plus one. I'm trying to find again. Nothing. Coming down. Yeah, what if I find one? If I find one, then it's at least this, right? So low, I think low shall equal to m. And a high, if it's, yeah. Because we're trying to find the maximum, right? So if it's good, so if it's not good, right? And so the maximum must be small, so high will be minus 1. And low plus high divided by 2. So this one biased towards low, right? If it's going to be this and this, so it has to be plus. Which means if I did find the right one, then lower always plus equal to 1, right? Lower always plus equal to 1. And I don't find it, and high will go down. And I'll find it, high go down, I'll find it, high go down, eventually we go. So I shall return low minus 1. Anyway, so if area, right, if area is equal to target, then I need to say found equals false. And we say found is a flag, true, then break, right? And I break out. With the else, which means nothing is found, then we just continue. Otherwise, we're going to break. Then I don't need this. I don't need a flag. I can just use this, right? So I say if we find the area, then I'm going to break it, right? I'm going to break it, and I will go here, then we break it again. So we have an else, or something, something, and then continue, and also this something, something. Okay. All right, let's handle the area first. Actually, we know how to handle area. Let's handle the logic first. What does else mean? Else means we go through the entire thing. We don't find anything. So nothing matches, right? If nothing matches, that means the mid is too high. So we're going to go high will equal to mid. Right? High, go down. And we continue. Otherwise, low equals mid plus 1. Right? Blah, blah, blah. We're going to turn low minus 1. So that is the logic for the end. So what is the area? Well, the area is the current area. So we say matrix ij, right? Matrix ij is current area. Current area, right? Minus, let's say if I'm here, minus this one, all right? Minus this one. So current area minus something, minus another something, and plus something. So this is actually where things got a little bit hard to deal, right? So it'll be nice if I have another layer. I don't have to do a lot of if and else check here. Are we gonna buy the bullet? Yeah, I think we're gonna buy the bullet. Okay, let's buy the bullet. So we say pref sum equal to 0 times n plus 1, right? And I'll do this for this in range m plus 1. To add another layer. Now we add another layer, we don't need this. And we can start from this. Actually, no. Let's start from here. Start from here. And this will equal to this plus previous one. That's the same thing, but because I do need to, but that's not matrix, that's just pref sum, right? Will equal to int this plus prefix pref sum this, right? And once it's done, this is going to be the same thing, and this is not going to be matrix. This is just going to be pref sum. All right. Now with this prefix sum, that's just going to be mn. All right, that's going to be m and n. The length is the same, target is the same, but this is not going to be mid minus 1. That is just going to be from mid, all right, to actually m plus 1. That can be mid to m plus 1. And for the minus, not matrix, this is a pref sum, right? With a minus pref sum. Now, ij is here, so I need to minus this one. This one is just I, j minus 1, right? So I, j minus 1. The next one is pref sum, I minus 1, j. So I minus 1, j is going to be, so I'm looking at here, hold on, that's actually not correct, because I am, I start from mid, like I start from here, so that's actually, no, that's not right. It's, let's say 2 by 2, so this is going to be this minus, I is the same I, but j minus 1 minus 2, so j minus mid, right? J minus mid, and same thing gonna be j I minus 1 minus I minus mid, right? So if I want to calculate this, it's gonna be j minus mid, so it's this and this, so it'll be I minus mid j and plus, because we minus this part twice, so plus, that's I minus mid, j minus mid. So this is going to be pref sum, I minus mid, j minus mid. So this is O1, right? With O1 we get the area, and we check the area, and blah, blah, blah. All right, let's try this. See how this one goes. Input is just matrix, so it'll be easy to handle. It's just a matrix, and the result is 4. Second one, the result should be 1. Yeah, I feel the binary search, there might be something wrong with binary search. It's possible. Not 100% sure. But I wrote it pretty fast, so it is likely I missed something. But let's try it first. Go. Syntax error. Where is it? Fuck up this. Go. Ooh, that is ugly as hell. What the heck? Alright. That is not cool. Alright, we'll comment out these two, and let's print out the prefix sum. For row in pref sum, and print row. Let's make sure this one is correct. That is not correct. That is not correct. It's because I forgot a plus 1. Right? I forgot a plus 1. What the hell? Oh, that is correct. It has to be minus 1. Alrighty. I think the prefix sum is correct. 1, 1, 2, 2, 2, 2, 2, 4, 5, 6, 3, 4, 7, 9, 11, 4, 5, 8, 11, 13. Okay. So the problem is I return 2. Oh. I have to return this one squared. Forgot I had to square it. Oh, boo! Yeah, that was terrible. Okay, so something is not right. Okay, edge case didn't pass. Why did I delete it? Why did I delete it? All right, I'm gonna do this. That is correct. So it's 2, and square root of 1. So we have 1, and going inside 0 smaller than 1, and this one mid is 0. Mid is 0. That is the issue. That is the issue. How do we handle that? Well, what we can do is set low equal to 1, all right? And we just check the high. Oh, not check the high, we check the pre-sum this, right? The only possibility that is 0 is this one is 0, right? If this is 0, then we just return 0. So special case, we say if this is equal to 0, then we just return 0. Easy peasy. If not, that means at least we can do 1. So that would be 1. Oh, it is still wrong. Alright, so in this case, one small, I probably have to change the logic. How? Oof. Maybe let's say high. What if I always go high is like larger than possible, like +1? Right? If it's larger than possible, then we are able to go inside. Then both will work. Right? All of them will work. Yeah, we go this one a little bit bigger, so they will always go inside, and something works, then alright, something works. That is the now this is the where that takes the longest time. Alright, I'm gonna try this one. It's very complex. Alright, come on. Oh, we passed it. So that is the solution. Well, but it's pretty slow, so it's gotta be something easier to do. So this one, first we create a 2D prefix sum. This allows us to query the area, query the sum of any rectangle, right, in O1 time. Then we use binary search. Binary search to locate the biggest square that contains all ones. The idea is that, right, if a mid value is, let's be more specific. So we start with the smallest size, smallest length of the square's side, and the largest length. All right, we start with these two, and we say if the mid-length square can be found, right, that means we can try a length, a longer length, a larger length. Right? You can try a larger length. Otherwise, we try a smaller length. So I think runtime is OMN log MN. That's OMN. This one, because of this, that's also OMN. In that, right? And then it's binary search, so it's log, right? This one, runtime is pretty miserable. 384 milliseconds with 13% linking. All right. This one has solution. So let's take a look at what the solution says. And also take a look at the spread. See what's the majority time is. Oh, pretty bad, huh? Pretty bad. About twice, close to twice as slow. Shoot. Brute force is accepted. OMN squared. Dynamic programming. OMN, single pass dynamic programming, or better dynamic programming. You can use dynamic program. I did not think about that. Let's see. Blah blah. dpij represents the side length of the maximum square whose bottom right corner is the cell. Okay. So this will be 3. This will be 2. This will be 1. Okay. Starting from this position, for every 1 found in the original matrix, we can update the value of the current value. For every 1 found, let's see, if I find this 1, then I need to know the length, right? The largest length. I know I'm 1. So if I know this is 1, and I know at least I have 1, I need to know this one, and this one, right? Hold on, let me think again. So I want to know, so if I go like this, right? And then I'm looking at here. How do I know? Well, I know this one's 1, right? There's no question about it. And I want to know what is this one. So I say I check this, and this is 1. And I check this is 1. Right, and I check this. So this one might have this one might have whatever, this one might have whatever. It's all going up and right, up and right. So I'll have the minimum of these because I'm going down 1, right? So the minimum of these, I mean, build a picture in my head. I find the minimum of these, the smallest, because the smallest that include the entire thing, right? Include the entire thing. Then I can add 1. Let me think again. It's saying is this position, and this position, right? And find the smallest among these 3 positions. Well, this position will give me this, and then how do I know by this? This, I see, this is 3, right? So I know this is a 2, 2, 2. So 2 means I have this. 2 means I have this. 2 means I have this, right? And in this position, I have 1. So this is just by itself. This is going to be 3. This is going to be 3. So it's determined by the smallest. That's true, right? It's true. We're determined by the smallest. If I have something, what if I have a small one here, and I have a huge one here, and a huge one here? It won't be, because if this was huge, this will be huge as well. All right? I still can't wrap my head around. Let me try one more time. So I have something of here, right? The largest square, and one right next to me. I have another one, right? And then down I have another one. So I say for the bottom right corner, right? Bottom right corner. The largest length I have is the smallest length. If I have this, I have this, right? And I don't want to have this. So it'll be the smallest one. Because if I have a big one here, but I have a small one here, then I cannot use the big one because there'll be nothing. So I take the small one, right? But why do I need the top corner? Would it be like a big value on here, but a small value on the top? I don't see it's possible. Is it possible? I have some value. I will have a small value here, right? I have a big value here. That's possible. Then my question is, why do I need this one? Right, if I have a small value here, which means only extend very little, so I can only extend very little. I need these two to guide me, right? To guide me how far I can reach. So this one says I can reach like until here, right? And this one tells me I can reach until some position. So I pick the smaller one, right? I can reach. And if I pick the smaller one I can reach, then I know I definitely can reach here. Because this one already tells me what it can reach. So I don't know why I had to do I minus 1, j minus 1. We only need one row, so we have previous row, current row, right? So these two are from the previous row. That's dpi. That's a dpi minus 1, and that's a pre, so I need a pre. Oh, wow. I think I still didn't get the insight. All right, so a top down. You say I'm gonna do a top down. What's the largest square one that begins with you? Okay. The largest squares. It's adjacent. cell can begin. So it'll ask the same question, yeah. I don't know, like maybe like around the edges we might need this. What if I have, oh yeah, like here, this position, this is 0, right? If I have 1 here, I have 1 here, this is 0, right? Then I am 1. I say I take the smallest of these two, they all extend, but only extend 1. Therefore, I need this. I see. Now I see. Good solution. Very good solution. All right, we're going to do this, so we're going to do it in the optimal way, right? We actually post the solution. That's fine. What do I say? This is a DP from the official solution. Let's post the link. All right, and then we say, what do we say? We say DP from the official solution. So dpij represents the largest square, filled with 1 that ends at ij position. All right, so we need a DP, and we realize DP only need to be, okay, mn equals len matrix, right? So DP is, I only need to do n, 0 times n, right? And then I have a DP, I have a pre, that's going to be 0. Now what we're going to do is for I in range m, j in range n. All right. So if matrix ij is equal to 1, then we're going to compute. And for each one, we're going to have a temp. Wait, do we need a temp? Let me think. So I have a DP, that's an array, that will represent the previous one, right? So I have a new value coming in. I will check with this. When we're done, then I put my value inside, right? I put my value inside, and that value will be the current one, is the new one. Yeah, I don't need a, I think that 1 DP is enough. So if that is true, then what we say? We say dp j, right? dpj will equal to because it's the pre. What is a pre? Pre is the diagonal, right? Pre is the diagonal. So dpj is equal to, we need to save pre, right? So pre is here. That's j minus 1, dpj, right? dpj minus 1, and this one is the previous value. How do we keep track of the previous value? Previous value is, so I need a temp. Temp is equal to dpj. That is the previous value for the next round, right? So dpj will equals the minimum plus 1. Minimum what? Minimum pre dpj minus 1. Right, that's to the left. And pre is the upper left. And dpj itself. And we're going to do n plus 1. So this doesn't change. This doesn't change. Yeah, matrix does not change. But dp, everything has to be plus 1, which actually makes it a little bit tougher to write. I'd rather do it here. So everything will be plus 1. And this is just going to be, oh, I doesn't have to change. Come on. I does not have to change. J change. I does not change. J change. So temp is going to be this. dpj equals this. And pre will equal to temp. Which I might be able to... Nah, it's too complicated. I just do this, right? Pre equals this. And eventually we want to find the largest. So we need a res. Oh, that's too cheeky. Res will equal to 0, right? So dpj equals this. And then res equals max res dpj. And then pre equals this. Once we're done, turn res. Res times 2. Yeah, this is OMM. Very good solution. Very good. Very good. All right, submit. Oh! Hold on. We got wrong. Ay, ay, ay. It was 4. All right, we need to take a look. What do we have? 1, 2, 3, 4, 5. 5 columns and 5 by 5. I think this is a 5 by 5. Okay. 1, 2, 3, 4. 1, 2, 3, 4. So first is all 1. Second is all 1. Third is all 0. Yeah, doesn't feel right already. And then it's all 1. And then it's all 1. Yeah, it should be 4. What go wrong? If matrix I, j minus 1, because j I start from 1. So yeah, if that's 1, then dp j. dpj, temp is dpj, and dpj equals pre, which is 0, and dpj minus 1, which is also 0, and dpj, which is 0, so it's 1, right? The first one, I'll get 1, and temp is 0. So pre equals, okay, I think this is the problem, the pre. How do we handle pre? For the first row, the pre will always be 0, right? Because there's nothing. In the second row, yeah, for the first row, pre will always be 0. So temp is equal to this if I, else 0. Nope. Still not right. Let's take a look at the DP after each row. So, oh, I just need one of them. Oh, sorry, that was wrong. All right, first row is correct, right? All one. Second one is 1, 2, 2, 2, 2, 2, 2, right? That is correct. So the first one is correct. Second one is correct. Third one, oh, if it's 0, then we should do 0. That is a problem. Else, dp j what equal to 0. Shouldn't we do the same thing? Yeah, hold on. Hold one second. I want to see how this one goes. Yeah, this one works too. All ones. I'm just trying to see if I need to do this. Pre. If it's all 1, you know what? This is necessary. So this shall be outside, right? And if this, then we do this, else dpj equal to 0. Then we do this. That's it. That's it. Forgot to set it back to 0. All right. Try it again. There we go. That is the solution. So let's go 200 milliseconds or 83. Ooh, nice, 83. Good, very good problem. Very good problem. Very good problem. Binary search.